Okay. So grasping is a long-standing problem in robotics research, and we'll be considering how to find good contact points on the object. And meanwhile, in fixturing, in manufacturing, you need to mechanically restrain a part for milling or drilling. So first, we're going to give some background and clarify how we're quantifying if a grasp is good. Then we're going to give the main contribution of the paper, which is an efficient algorithm for finding good grasps. And last, we're going to show some examples found by the algorithm for grasping and fixturing, and also an application to towing. So this is just an illustrative example. This is a two-dimensional object that you might want to grasp, and two different ways of choosing 4 contact points on it. So they both have force closure, meaning that for any disturbance, any wrench that you apply to the object, you can resist that wrench by applying forces at the contacts. But the one on the left is better because it's better at resisting downward disturbances. And if you apply a downward force on the right, the 2 contacts on the side will have to apply a lot of force. So so the quality metric quantifies this idea, and the grasp has high quality if you can resist large disturbances by applying small forces at the contacts. So here at the bottom, I'm showing you a slice of wrench space, and I'm just showing you the force components, the force in the x and the y direction of wrench space. There's also a torque component. And these red vectors here, these red arrows are the forces resulting from the wrenches resulting from unit normal forces at the contacts. And the gray area, so we're going to consider this quality metric called Q infinity. And the way it's defined is you put a force limit on every contact. You say you're only allowed to exert 1 unit of force at every contact. And then you basically look at the size of wrench space that you can resist, of disturbances that you can resist. So here, the gray area shows the size of wrench, the set of wrenches that you can produce given this force limit. And the Q infinity quality metric, I apologize if people in the back can't see this, is defined as the smallest wrench that can't be resisted given these force limits. And it has a geometric interpretation as taking this set of wrenches that you can produce and taking the biggest circle centered at the origin that lies inside that set. And Q infinity is the radius of that circle. It's called the residual radius of the set. So our problem is formulated as follows. We're given a shape and a set of candidate contact points, and we want to find a k-element subset that maximizes the Q infinity quality metric, which is the residual radius of this set. So our contributions are as follows. We derive new formulas for the quality metric, and the new formula can be evaluated using a discretization approximation. Then we show that the problem, we can use submodularity and use the submodular saturation algorithm to efficiently optimize the quality metric. And this algorithm makes it practical to choose a large number of contact points on an object, for example, to fixture a delicate object, whereas previous algorithms for generating force closure grasps usually focused on finding the minimal number of contacts necessary for force closure. So here I'm just going to give a sample of some of the previous work on grasping, including the work that we build on. So the first ideas of force closure are due to Rouleau in the 19th century. And then Mishra, Schwartz, and Sharir proved a lot of the results about how many contacts you need for force closure. Then two papers, one by Ferrari and Canny and the other by Kirkpatrick, Mishra, and Yap, introduced the quality metrics that we consider. In particular, the Q-infinity quality metric was defined by Ferrari and Canny. So these papers on the quality metrics left two open questions. First of all, how do you efficiently evaluate these quality metrics? And second of all, how do you select the contact points that optimize them? And Borst, Fisher, and Hertzinger worked on the first problem. They gave an efficient algorithm for evaluating the Q-infinity quality metric. That's an approximate algorithm. And Teichmann and Mishra addressed the second problem. They showed when you specialize to the frictionless case, they gave a fast algorithm for optimizing actually an easier quality metric. And recent work on grasping has proceeded along a bunch of different angles between designing fixtures for parts to designing stable compliant grasps, grasping under uncertainty, planning with kinematic constraints of a hand, or dealing with clutter. But we're actually going to go back to this, the earlier definitions of the quality metrics, and we build on some recent results in combinatorial optimization to show that you can efficiently optimize the quality metrics. So in our optimization problem, we're trying to choose k contacts out of n candidates. And there are no formal results about the hardness of this problem, but a naive search would take too long in most cases, since you have order of n to the k ways of selecting these contacts, and for each choice you have to evaluate this quality metric, which is a non-trivial calculation in itself. So we're going to reformulate the problem, and essentially this gives us a different way of calculating Q-infinity that's fast, and it reveals that the problem has a nice structure that we can exploit. So in the original problem formulation, we've got these friction cones resulting from each contact point, and then the set of wrenches we can produce under force limits is given by the Minkowski sum of these friction cones. That's illustrated as the gray region. And we want that set to have a big residual radius. So it turns out there's another way we can calculate the residual radius. And I'm not going to prove this formula, but I'm going to try to give a little bit of intuition about it. So let's consider a certain direction in wrench space, shown a certain unit vector in wrench space, shown by the blue vector. And take the projection of all your friction cones onto that direction, and take the positive part of those projections, and then take the sum of those positive parts. So that essentially tells you, so each of those projections tells you how much a given contact can contribute to resisting a wrench in that direction. So when you add them all together, that will sort of tell you how much all of your contacts can help to resist a wrench in that direction. So it turns out that if you take that sum in, for all directions in wrench space, and you take the minimum over all directions, then that tells you the residual radius of your set. And the nice thing about this formula, which involves minimization over direction of wrench space, is that we can approximately evaluate it by discretizing that unit sphere in wrench space. So by discretizing the unit sphere in wrench space, we can approximately evaluate the quality metric. And so now I'm going to show that this problem is what's called a submodular coverage problem. So submodularity is a diminishing returns, is a property of set functions that means that they have a diminishing returns property. If you add an element E to a small set A, you get less of an improvement to your function than if you add an element to a bigger set, A union B. Submodular coverage problems are what you get when you take a minimum over a set of submodular objectives. So it's like you choose your subset S, and then an adversary chooses which of your objectives gets evaluated. And in our case, the adversary is choosing which direction, which disturbance wrench is being chosen. So our adversary is choosing a disturbance wrench, basically. And our submodular objectives are the sums that I showed on the previous slide. So Krauss and collaborators recently showed a clever and pretty simple algorithm that optimizes these submodular coverage problems, and the solution is near optimal with the performance guarantee. And the time is roughly linear in n, the number of candidates, and k, the number of selections, which is obviously much better than n to the k for brute force enumeration. So the complete algorithm that we can use to select contact points on a 3D object is as follows. We select candidate contact points, which are just points on the surface of the object that are accessible, and we calculate the contact wrenches that result from applying forces at those contact points in the friction cone. And then we pre-compute a table of values which tells you how much each contact can contribute to resisting forces in a certain direction in wrench space. So we have one pair for every contact in every direction in wrench space. And then once we've computed this table of values, we use saturate to solve an optimization problem. So here I've just shown examples in 2 dimensions for illustration, but this method is well suited for 3-dimensional objects and various contact models where your contacts have Coulomb friction or soft finger contacts, or if you're selecting among surface or line contacts. The method also works on the Q1 quality metric where you're constraining the sum of forces at the contacts. And you can also use the method on a more general problem where you know a set of disturbances that are going to occur during your task, and you want to resist these disturbances with as little force at the contacts as possible. And the disturbances may include a constant component like gravity. We ran some numerical experiments testing out the algorithm on 3D models taken from the Princeton Shape database, which is a standard benchmark data set. So saturate gives, so we chose problems where we actually could find the optimal solution in a reasonable amount of time, and on these problems saturate gave a near optimal solution. The runtime was roughly linear and very modest, taking only tens of seconds even for a large number of contacts.